Let's talk about how servos work and what kinds of signals they get from our extension board. So let's turn this on. And I've got this set up so that I can switch between 0 degrees and 180 degrees. 0, 180. So that makes this little guy just turn right around. Let's look at what signal makes the servo do that. So let's unplug the servo and let's plug in instead our oscilloscope. Turn it on. Turn this on. And there we go. Hi, macro mode. See if I can get this to focus. Will you focus? Yes or no? There you are. Okay, so as you can see, down in the left corner, it says that the pulse is 480 microseconds wide and the frequency is 51.8 hertz. That's 51.8 times per second. That's what that means. And it's producing a logical on and a logical off. At 0, it is logically on or logically off, and at 3.3 volts thereabouts it is logically on. Okay, so let's switch now to the other 180 and let's look again. As you can see now, the pulse width is 2.4 milliseconds. Frequency is still 51.8 or 9, and it's still running at about 3.3 volts. But what you see is that when we switch from 0 to 90, the width of the pulse goes from 500 microseconds to about 2500 microseconds. That's what the servo expects to get to turn from 0 to 180 degrees. We're not seeing exactly that. And the reason for that is this little chip right inside here. It is a PCA 9685 chip, and it is that one right there. That's our chip. It's capable of generating pulse width modulation signals, and that's what that is. So we're generating a pulse and we're changing the width to tell the servo which position to go to. Pulse width modulation, meaning we're going to change the width of that pulse back and forth to change the position of the servo. Right? Pulse width modulation. And you see that abbreviated as PWM everywhere pretty much. Okay, so that is what causes our servo to move. Now, as we saw, it isn't quite accurate. And the reason for that is that these chips, the PCA 9685, is extremely cheap. So it's not very accurate, basically. And on top of that, these servos are also extremely cheap. So they're not very accurate either. So given all that inaccuracy, we can't really move a program from one robot to another, identical robot, or somewhat identical without changing a whole bunch of numbers. And we'd like to avoid that if we can, for the kids' sake. Now, if you're one student with one board and one robot, then you're just going to have one set of calibrations, right? But if you are a classroom teacher and you've got multiple robots, standardizing is going to be beneficial to you. That way, the kids can take their microbit out, put it into a different robot, and it will work if they change the calibrations. Right? If they choose a robot like Rosie here, this is Rosie, they can set Rosie's calibrations up, and then Rosie will work. So why does that matter? Well, if you have students making these robots, and these robots get fairly complex as we go through the curriculum, if a student, for some reason, totally messes up the build portion of the assignment, and it's all glued together and it can't move, and that student is going to have to start over. If we're 2 weeks in and that student is starting over on the build, that's going to be an issue, right? Because now they're not starting the programming with the rest of the class starting the programming. So now they're way behind. In a case like that, if you have several robots, BB, Rosie, and Daisy, for example, you can say, here, tell you what, put your robot aside and just program Daisy. Because I know Daisy works. Now, if a student, for example, breaks their robot, you might be hesitant to give them one of yours, but you might need to say, okay, let's put your robot aside because we don't want to spend time fixing it, and let's use one of the classroom robots to finish the assignment. So that's why we're trying to standardize on certain calibrations. So that's the justification for doing that. And because the servo and the board have their own types of errors, we're going to want to isolate those so that any board can work with any robot given the correct calibrations of the two. So we're going to have a calibration for the board for this particular chip, and then we're going to have calibrations that work for the servos. And when those combine together, the robot will respond, the different robots will respond in exactly the same way. Now, how will that work? Let's look at that. So here is the program that runs the BabyBot, and we're going to go down to the babybot.py. We're going to take a look at what's in here. Here I have settings. These are the calibrations for each of the 3 classroom robots. And the students would then add their own robot in here, and then if they needed to, they could go back to their main program, and they could, when they initialize their robot, they'll call out whichever robot they're using, in this case, Daisy. And that will make the robot respond exactly the same, given, this is the other part, and I will be giving them this as starter code. we work in percentages. So moving the eyes from right to left is a percentage from 0 to 100. Lids up, down, 0 to 100. So they're going to have all of these percentages that they're going to be looking at. So let's look at blink, right? So making the robot blink, lids down to up, 0. 0 is down. Lids down to up, 100. Up is 100, right? So that causes the robot to blink. And these particular amounts are abstracted so that we do not actually have the angles called out. So they're going to be using these abstracted numbers. And if they select the right robot, use the right calibrations, here's BB, if they use the correct calibrations, they will run the same on any robot that we have. Any robot in the classroom, as long as the calibrations are correct, the program that they've created will run on that robot. We can even swap around the calibrations for the expansion boards if we need to. So the expansion board is not tied to a specific robot, and we have expansion board and servos calibrated separately so we can mix and match. If you needed to swap somebody's expansion board out because they shorted it out or something went wrong with it, you could do that if you know how to calibrate it. So let's look at that now. We won't be talking about calibrating the servos. We'll be showing that when we actually do our builds. So the first way to do that, and let's look at our main program here for this one. Is we simply we import this fine prescale, we tell it which servo to start with, and it's going to start out with the default prescale. I better tell you what the prescale is. All right, let's talk about the prescale, because you don't understand what I'm talking about. Okay, so prescale is a lot like how many seconds are in a minute, right? You get to you count 60 seconds and then you get a minute. Prescale is like that too. So let's look at pennies. So we've got 0, 1, 2, 3, 4. We get to 5 pennies, we can roll that over into a nickel. 0, 1, 2, 3, 4, 5 pennies. Roll that over into a nickel. Right? And so on. Another nickel. That's what this little PCA 9685 board does. This board, now if you look at this clock, grandfather clock, you see it over there next to the cat, it has a pendulum that goes back and forth, right? And it marks out the seconds. Well, this has an electronic pendulum inside it. There's a little quartz chip, a little piece of quartz in there that vibrates electrically, and it's supposed to vibrate at 25 megahertz, which is 25 million times a second. And the prescale is the count. So we're going to count from 0 to 121 vibrations in the quartz, and then we're going to roll over. And those are going to become segments. So instead of pennies and nickels, we have prescale and segments to worry about. Now, we can change the prescale, but we can't change the number of segments. There are 4,095 segments in each time it starts over. So the distance between pulses is divided into 4,096 segments. And we can turn on at a specific segment, and we can turn off at a specific segment. So we can turn our output to 3.3 volts, which is logical 1, and then turn it off. And based on the number of segments, which means that the length of that pulse is tied to the frequency that that chip is producing, right? Because if it's running at a nice pure 50 hertz, then those pulses are 20 milliseconds wide. 20 milliseconds wide, or 20,000 microseconds wide. And then when we divide that into 4,096, we can turn it on and turn it off, so we get approximately the right amount, right length of our pulse. What that means is that if it's not, then the width is not the same. So now let's say that we want 50 hertz. Our pulse is going to be 20 milliseconds wide. But let's say our pulse, we have a frequency of 52. Then our pulse, the width of our pulse is only going to be 19.1, it's going to be 19.3 milliseconds wide. So 10% of 2 milliseconds is very different than 10% of 19 milliseconds. So that's a problem, because our servos, remember, depend on the width of those pulses to find their correct angle. Okay, so I've written this little program called Find Prescale, and that's going to be in, I'll attach this file to it. And that allows us to set this. So when we touch the logo, it's going to switch from 0 to 180. When we touch button A, it's going to reduce the prescale. When we touch button B, it's going to increase it. As I said, the default, if this chip is truly running at 25 megahertz, then 121 is the prescale we need. That's what we're going to count to in pennies. But if it's not, then we need to find what it is. All right, so let's start that up. Turn on our bring it over here where you can focus. All right. Now you can see it's at 51.9. Let's change the prescale a little bit. We're going to increase it. 122, 123, and you can see the frequency going down. 124, 125, it's 50.2, that's really close. Let's see if we go one more. 126. Now we're at 59.8 hertz. But the nice thing is we're at 500 500 milliseconds, which is that number, microseconds, 500 microseconds, that's the number we want when we're at 0. Let's switch over to 180 degrees. What do we have now? We have 2,500 microseconds, which is also very close to what we want. So for this particular expansion board, 126 is the prescale we want. And so what we're going to do is we're going to mark that on the bottom of the board. Prescale 126. And that's the easy way to do it with an oscilloscope. You just basically move it up and back until you find a frequency output that is close to what you need in terms of the pulse width between 0 and 180 degrees. Find out whichever is closest. Now remember that because we're counting with integers, right? We count 1, 2, 3. We don't have half pennies. Right? There's no such thing as half a penny. The same is true with this expansion board. The prescale is an integer. There's no 121.5. There's 121, there's 122, 123. So whatever is closest is the one you're going to choose. And it should be close enough. It should be close enough. It's only a few microseconds difference. So it should be close. Now, what if you don't have an oscilloscope? How are you going to do this? How are you going to calibrate these boards so that they all work the same? Well, you can use a reference servo. So this is going to be my reference servo. Now, you don't want to use just any servo. You want to use one and only one servo. So choose one, doesn't matter which, really, but you want to use the same servo for each calibration. And the first build has space for you to cut this out of cardboard, put it on. I've drawn a vertical line across it. And what we're going to do now is we're going to look for it to go between 0 and 180. Now you'll notice that this does not line up with the 0. It does not line up. Why is that? Well, here's another compromise. We don't need you, nickels. The spline, as they call it, this little gear is a gear, and it has a certain number of teeth. And this servo horn, as they call it, also has a certain number of teeth. So usually there's usually 21 teeth on there, which means there's only 21 positions that it can go to. So if we take 360 degrees and we divide that by 21 teeth, we get just slightly over 17 degrees for each tooth. What does that mean? Well, that means that when you set this to 0 and then you try to put this on there, we're talking about plus or minus like 8 degrees. So the closest you're going to get is like 8 degrees. Within 8 degrees. So when we put this on here, it's not going to be exactly right because of those teeth. So what we're going to do now is, given that this is the way it is, we're going to switch to 180. And as you can see, it didn't go 180 because this was a little on this side and this is not a little on that side. So we're going to go ahead and increase, go to 122. Let's see what we got here. And I want to look straight down at it. There we go. That is actually about 180 degrees. Now that's 122. And you'll notice that if we go all the way up to the calibration we got with the oscilloscope, which is 126, you'll notice that it actually goes farther than 180 degrees by a little bit. That's because servos are not necessarily calibrated correctly. They're cheap. But the important point is that if you calibrate all of your expansion boards the same way, using the exact same servo, if you switch servos, they're not going to match up because every servo is different. Use the same servo, tape it to the cardboard so you know which one it is. If you calibrate these so that the servo travels from 0 to 180, then all of the expansion boards will be the same. They'll operate the same. And that's really all you want. You don't need them to be precisely accurate. You need them to all be the same. And that's what we're looking for. So here are two ways to calibrate your expansion boards so that you can essentially have them all behave the same. Now, once you have your expansion boards all behaving the same, then when you take something like BB the robot, then you're not going to push those servos past what they ought to be. See, now the eyes, the head movement, those all have limits. If you push the servo beyond those limits, you can snap off the linkages internally, and that is a real pain to have to go back and oh, bless you. So, oh my gosh, you're sick today. I'm sorry about that. Poor baby. And so we're going to calibrate the servos separate. Like I said, we'll have a set of calibrations for this robot, and we'll look at those again. Here, baby bot. These are the calibrations. So these calibrations take into account the differences in the servos. And this number right here, that's our prescale. So you can see it's called out as our prescale. Now this would change if we swap the expansion board. That changes. But if we've got them, connected together, they come as one unit. You can say here's BB. Use BB's calibrations. Plug your microbit in, and it should work, because again, the kids are using an abstraction. They're using percentages instead of actual servo angles, which, as we've learned now, is not necessarily the angle that the servo is going to be at. There's too many variables. But we do want to have some standard way of talking about this and overcoming it, so that our code is independent of the robot. And again, that's so that if a student's robot breaks halfway through the coding, you can walk over with a classroom robot and say, here, switch to the calibrations for this robot, and continue programming. Okay, I think that's enough for this time, and I'll see you next time. Thanks for watching.